Hi, everyone, and welcome to this webinar organized by Docsity in partnership with Syracuse University, Whitman School of Management. I'm Alessandra, nice to meet you all, and I'll be your host for today's event on behalf of Docsity. So I see here that the first people are starting to join in, so we're going to wait a few minutes before starting to allow everyone to connect. And in the meantime, feel free to say hi here on our chat on Zoom. And first of all, I want to thank everyone for joining us and especially thank our panelists for being here today. I want to introduce you to Professor Anna Chernobai, Professor of Finance at the MJ Whitman School of Management at Syracuse University. And today we're gonna see together with Professor Chernobai statistical inference, and we're gonna learn more about data analytics. So to talk a little bit about Professor Chernobai, her research focuses on operational risk, default risk, stochastic processes, and applied statistics and probability. She has published in top finance and related journals, such as the Journal of Monetary Economics, Journal of Finance and Quantitative Analysis, Journal of Banking and Finance, MIS Quarterly, and Journal of Accounting Information System and Real Estate Economics. And she also published her own book, which is titled Operational Risk, A Guide to Basel II Capital Requirements, Models and Analysis in 2007. Dr. Chernobai's teaching experience includes undergraduate, MBA courses, and also PhD seminars in the areas of risk management, business statistics, data analytics, and stochastic processes. So as I already told you, together with her today, we're going to explore today's theme, which is how to master statistical inference, unlocking the power of data analytics. And during the masterclass, we're going to learn more about statistical inference. We'll cover the central limit theorem, confidence intervals, and hypothesis testing. So we'll learn how and why data experts use data samples and how they extrapolate information to describe whole populations. So I'd like to remind you that after the presentation, we will have a Q&A session where you'll be able to ask direct questions to Professor Chernobai. So don't be shy and just type all of your questions, doubts, and curiosities in the Q&A section here on Zoom, and then we will be happy to go through them at the end of the webinar. Also, for those interested in receiving a certificate of attendance by Docsity for the masterclass, stay tuned because we will be posting the link to get the certificate at the end of the session. So I see here that people are joining in. Welcome you all. Welcome to those who just joined. And I think that without further ado, I'm now leaving the floor to Professor Chernobai. So thank you, and we will see each other later. Enjoy.
Good afternoon, everyone. My name is Anna Chernobai, and I'm with the Whitman School of Management. Let me share my screen. And let me share the presentation. Okay, can everybody see the presentation? Okay. So today we're going to be talking about statistical inference, which is a topic in statistics that students, both undergraduate and graduate students, struggle with the most. Here at the Whitman School of Management at Syracuse University, I teach at the undergraduate and graduate levels. Currently, this semester, I'm teaching 2 master's level courses on statistics, probability, and regression analysis. In one of the classes, we use Excel as the software. In another class, we use R. And so let's get started. Okay, so first of all, why do statisticians use samples of data and not populations when they make inference? This is very important to make a clear distinction between what is a sample, what is a population, because the entire topic of statistical inference is built upon this distinction. So we need to have a very clear understanding of what is a sample, what is a population. Okay, so population is all objects of interest. Okay, so for example, all companies in the United States, all master's students in the United States in 2023, or all voters in presidential elections. And the sample is just a subset of that population of interest. So we may have one sample taken from this portion of the population, another sample taken from here, another sample from here, or we might have a more representative sample like this one. So why do statisticians not work with populations? Well, the reason is actually very simple. It's just because of practical considerations. Usually populations are simply very, very large. And trying to collect data from the entire population is either impractical or too costly or too time-consuming or simply impossible. So statisticians, they resort to just collecting a sample, a subset from this population, and kind of generalizing their results that they find to the entire population. So to make inferences about a population, a sample is studied. Ideally, we would like to have a sample that's a random sample. So we have objects like here that are randomly taken from the entire population that go into a sample. And also, it may be quite an intuitive result. A bigger sample is always better than a smaller sample because a bigger sample is closer to the entire population of interest. Then we can summarize population and sample. So summaries of population are called parameters. So here we can talk about summaries such as population mean, population standard deviation, population variance, population proportion. And notice how we usually use Greek letters to denote population parameters. For samples, we can compute similar quantities, but using different formulas. And these are typically called statistics. So we can compute quantities such as sample mean, X bar, sample standard deviation, S, sample proportion, p hat, so on and so forth. What's important is that because we have only one population, then the parameters are constant values. So it's just one population mean, one population standard deviation. But samples can be different. We can have a sample from here, sample from there, sample from here, or a random sample like this one. And because of that, sample mean, sample standard deviation, proportion, so on and so forth, all of these statistics that are based on samples are random variables in the sense that they can take different values depending on which sample is taken from our population. And this becomes very important in inference. So that's why I wanted to show you a couple of basic review slides about population and sample, because this becomes very important later on. Okay, so in any statistical study, there are two phases. The first one is descriptive statistics. That's when we collect the data for what we want to study and then summarize data. So the way we summarize data is by creating charts such as a pie chart or a histogram or a box plot. And then we also compute numerical summaries of our sample data, such as sample mean, standard deviation, proportion of data that meet this and that characteristics, so on and so forth. And then there is inferential statistics, which is going to be the focus of what we'll be talking about today. So here we analyze data and make statements about the entire population. And here we can use a variety of different inferential techniques, such as hypothesis testing, confidence intervals, regression analysis, t-test, f-test, so on and so forth. So what is statistical inference? Imagine we have a population, and like we said, it's not possible to collect data from the entire population because the population size N is very, very large. We can assume for practical purposes that it's infinite. And this population has parameters such as population mean, population standard deviation, proportion, so on and so forth. From this population, we collect a sample. Hopefully it's a random sample, which would make it representative of the population. And for this sample, we can compute sample size, let's say it's 100, sample mean, let's say 3.1, sample variance, such as 2.7. And then what inference is that we use data from the sample to make some conclusions or predictions or inferences about the unknown population parameter. So more formally, statistical inference is when we use information from a sample to make some conclusions about an unknown population parameter. And typically, the way inference works is that at the core of any kind of statistical inference is the sample counterpart of what it is we are trying to understand. So if we are trying to make inference about the population mean, then we need a sample mean that would be the core of our statistical analysis to make the inference. So we always use sample counterpart of what it is that we are trying to understand about the population, and the entire procedure of our statistical analysis would revolve around this sample counterpart. Okay, let's jump to an example. And this is an example that I show in one of my classes that I teach here. Suppose we want to know the average number of job interviews that master's students got this year in the USA. So clearly what we're interested in is the average for the whole population of all master's students in the USA. And the population mean the average number of job interviews is what we want to try to figure out. Well, clearly it's not possible to ask every single master's students in the USA, how many job interviews did you get this year, and then compute the mean of those numbers, because it's going to take us forever, or it's just not going to be possible to get in touch with every single student. So we collect data from a sample. We ask maybe only students at Syracuse University how many job interviews they got. So we use sample mean, so the mean we obtained in the sample, to estimate this unknown, the population mean. So in that sense, because we are using sample mean as just one number, we call it a point estimate of population mean, just 1 point, one data point. But clearly, because this is just a sample and samples might be different, so we might get a different sample mean value from a different sample, using sample mean as a point estimate of population mean comes at a cost. There is an estimation error, also called sampling error or standard error. So there is an error that comes with using sample mean as a point estimate of population mean. So in inference, we often hear concepts such as law of large numbers and central limit theorem. Let's discuss what they are. So law of large numbers is, the way it works is, so we have a population, and let's say from this population, for this population, we know that the population mean is 3.8. Let's pretend that we actually know the true number. So from this population, we collect a very small sample, let's say size 3. We calculate the sample mean, and it's 3.1. It's a little bit far away from the true population mean. If we collect a bigger sample of size 15, then when we compute the sample mean, it's going to be 4.5. It's still pretty far away from the true population mean. Then we collect a bigger sample, let's say size 300 data points, and then we compute sample mean, it's 3.9. It's getting a little closer to the true population mean. And then if you take it to extreme and collect a really large sample, let's say 2,000 observations, and we compute the sample mean, it's going to be very close to the true population mean. So to summarize, law of large numbers basically says that when sample size goes to infinity, when sample grows in size, then the sample mean approaches the population mean. And also, statistical inference will become more and more accurate for larger sample size. So let me show you an Excel file that I show to my students when I talk about law of large numbers. So here in column A, I have my population. So we have different X values. And here we have a total of 40,000 observations. So let's pretend that this is our entire population. And suppose we know that the true population mean is 1.65. So on the graph, 1.65 is the population mean. It's this straight line here. And then from this population, we start taking samples, random samples of size 3, 8, 10, 11, 12. And for each sample of this particular size, how many data points, we compute the sample mean of those values. So this is what we have on the horizontal axis. On the horizontal axis, we have sample size, 1, 2, 3, 4, 5. And these sample mean values based on those sample sizes is what the green line is. And notice that when sample size is small, the sample means are quite far from the true population mean, and it's also much more volatile. But then we're approaching more and more the true population mean as sample size increases. Let me try to draw other random samples from this population and notice how the picture changes. So I'm just going to keep changing it. So you see that the pattern remains the same. We have a lot of volatility and uncertainty for small sample sizes, but for larger sample sizes, we are not that far away from the true population mean. Okay, so this is what law of large numbers is all about. Okay, so the second important concept in statistics is essential limit theorem. And essential actually means something important. So it's so essential to statistics that we have to talk about it. This is what essential limit theorem is. So again, let's start with the population. So the variable of interest, the main variable X, is number of job interviews. So imagine that this whole population consists of a ton of data points. Each data point shows how many job interviews a particular master's student got this year. And suppose we know that the true population mean is 3.8. So this time we're going to proceed a little bit differently. So we're going to collect a sample of size 100. So 100 data points in this sample, and we compute the sample mean, and it's 3.9. Then we collect another sample, also size 100, and we compute that mean, and it's 4.2, slightly different value. We collect another sample, a sample mean is 2.4, another sample mean is 5.1. We can continue like this on and on and on. We can collect a gazillion different samples of the same size, and every time we're going to get a slightly different sample mean value. Can anybody guess what, on average, if you take the average of all of these sample mean values, can anybody guess what we're going to get on average if we take the average of sample averages? Well, the answer is, on average, we're going to get it right. The average of all of these sample averages is the unknown population mean. So we notice that sample means can take different values depending on the outcome, depending on the sample. And what do we call in statistics a quantity that can take different values? We call it a random variable as opposed to parameter. So population mean is a parameter, sample means are random variables, okay? What does it mean that something is a random variable? We can use, for example, a histogram to plot the distribution of this random variable. We can see how it's distributed. We can also compute its mean. We can compute its standard deviation, variance, so on and so forth. So the essential limit theorem says that if a random sample of size n is drawn from any distribution that has mean mu and standard deviation sigma, then when sample size is large, specifically at least 30, then sample mean is approximately normally distributed with the mean of sample means equal to the true population mean, and the standard deviation of sample means equals to the standard deviation of the whole population divided by the square root of sample size. Let me go back one screen. Okay, so I'm going to show you another picture that I showed to my students, essential limit theorem. So this is where essential limit theorem is explained. So here we have our population X. Notice that it's right skewed. The distribution is right skewed. Remember, essential limit theorem says that any distribution would work. It doesn't matter what the distribution is. So here it's right skewed, and suppose we know that the true population mean is 1.65. So suppose in this blue area of the Excel spreadsheet, so here we collect a lot of different samples of size 10. Sample 1, sample 2, sample 3, sample 4. Each one of them has 10 data points. And for each one of them, we compute sample mean. So we collect all of these sample mean values, we put them on the horizontal axis, and then we plot a histogram that shows the frequencies of these sample means. Notice that compared to the original distribution of X, this is much more bell-shaped. It's closer to being symmetric, but it's still quite far away from that. And then here in the green area, we collect very large samples, bigger than 30 data points in each, specifically sample size 100. So we get a bunch of samples, sample 1, 2, 3, 4, 5. For each one, we calculate sample mean. We put them on the horizontal axis, create a histogram. Now it's approximately normal. It's approximately normal. In the middle of this bell-shaped curve, we're going to have a true population mean 1.65. You can see it somewhere around here. We can repeat the same by generating different data, generating different samples, but every time you'll see the same pattern emerges. Sometimes we get closer to the true bell-shaped curve, sometimes we're a little bit further away, but the overall pattern is clear. When we collect data, large samples of data, then sample means will follow approximately normal distribution with the mean of this distribution equal to the true population mean and the standard deviation equal to sigma over square root of n. Okay, so let's move on. Okay, so when we collect a sample and compute its mean, clearly the whole point of doing that is we want this sample mean to be as close as possible to the true population mean. Whatever we get from the sample mean, we want it to be, ideally, we want it to be the true population mean value. We know it's not going to be the case, but we want it to be close to the true population mean value. So here, larger samples are better than smaller samples. Intuitively, it makes sense, but let's try to understand better why. So specifically, what happens is larger samples are better because the probability that the observed sample mean is within a very short distance away from the true population mean becomes higher for larger samples. So the probability that you're very close to the true population mean is larger the larger your sample. And here is an Excel spreadsheet for that I show in my classes. Okay, so we have a population X with this mean 50, standard deviation 15, and we collect samples from this population, random samples. And one example is a relatively large sample of size 100, but then another example is for larger samples, let's say size 200. So what are the properties of sample mean? So based on these formulas, the mean of sample mean is just the population mean. So regardless of the sample size, the mean of sample mean is just the population mean 50. But the standard deviation of sample mean actually depends on the sample size. It's going to be equal to the sigma 15 divided by the square root of 100 or square root of 200. And notice that for larger samples, the standard deviation of sample mean is smaller. Why? Because mathematically, the denominator increases, so the whole ratio falls. So let's look at this picture on the right. So we take a sample, we calculate what the sample mean is, and we want this sample mean to be very close to the true population mean. So here we are looking at what's the probability that the sample mean that we get is going to be 1 point away in either direction from the true population mean. So if the true population mean is 50, we are talking about the distance between 49 and 51. So if we collected a small sample, then there is a roughly 50% chance that we are 1 point away from the true population mean. But if sample size is 200, then this probability increases to 65%. So for the smaller sample, the probability I'm talking about is this area under the blue curve, which is roughly 50% of the entire area under the blue curve. But the 0.65% is this red area. Well, here it becomes kind of purple. So it's this area under the red curve, which accounts for roughly 65% of the whole area under the red curve. And now what I'm going to do is I'm going to increase this sample size. I'm going to make it even bigger. So notice what will happen in this picture, and particularly pay attention to this number, how it's going to be changing. Okay, sample size 300, 400, 500. Notice that this probability is increasing. 600, 700, 800. Let me go to 1500. Okay, so that, okay, let me go to 2500. Okay, here, let's stop here for now. Okay, when it's 2,500 observations in one sample, then there's practically 100% chance that we collect a sample, compute the sample mean, and this mean is just 1 point away from the true population mean. So this is why larger samples are always better than smaller samples, because our inference, our ability to use sample mean as the point estimate of population mean becomes more and more accurate. Okay, let's go back to the slides. Okay, so let's look at two approaches, two methodologies that are very widely used in statistical inference. One is confidence intervals. Let's understand what they are. So we're going to start with the same example. We want to know the average number of job interviews that master's students got this year in the USA. We want to use sample mean to estimate the population mean. So sample mean is the point estimate of population mean. It's at the core of any inference about the population mean. Okay, but what we already know is that such estimation using sample mean as a single point to make inference about the population mean, such estimation comes at a cost, which is called estimation error or sampling error or standard error. So instead of using sample mean as one data point to estimate the population mean and having to pay high cost for that, instead of doing that, what we can do is instead construct an interval estimate of the population mean that we are highly certain about. Yes, it's not going to be one single data point, but it's going to be an interval estimate, but it's also going to be an interval estimate that we are highly certain about, such as 95%. So it's going to look something like this. It's an interval, which is a range of values from A to B, even though it's not just one single data point, but a range of values, but it's such a range that we are very, very certain about. So we are going to be able to say something like, I'm 95% confident that the true population mean is somewhere in this range. Ideally, this range would be narrow. Okay, so let's look at how the methodology works. So 1 minus alpha percent confidence interval for mean is this formula. In my class, we actually derived this formula from scratch. So what is 1 minus alpha? So if our confidence level is 95%, then alpha is the 5% that we are missing, or 0.05. So think about it. If we are 95% confident about our estimation, then it means that we are willing to accept the error of 5%. We are willing to take the risk that there is 5% chance that we might be making a mistake. Okay, this is the formula. What's this Z value? In my class, we talk about it in detail, but this Z value is basically dictated by this level of confidence. So if you have a standard normal distribution, it's basically a high percentile of this standard normal distribution. So for 95% confidence level, 0.95 is the area in the middle, and alpha is split in half, 2.5% here, 2.5% here. So this point is essentially the 97.5th percentile of the standard normal distribution. Standard normal distribution is a normal distribution with mean 0 and standard deviation equal to 1. Okay, so how often, let's think about it, how often does it happen that population mean is something that we don't know, but the population standard deviation we miraculously do know? Well, this kind of stuff rarely happens. So in practical applications, sigma is also unknown. So what can we do? So we don't know sigma, the standard deviation of the population. So we're just going to go ahead and replace it with what we can find from the sample. And from the sample, we can compute sample mean and also sample standard deviation. So we replace sigma with sample standard deviation, and the formula becomes like this. So instead of Z, instead of standard normal distribution, we're going to use something that's called a T distribution. Normal distribution has two parameters, mu and sigma. T distribution here has one parameter called degrees of freedom, which is sample size -1. So T distribution actually looks very similar to the standard normal distribution. It's also symmetric around 0. It's a little bit more heavy-tailed than the normal distribution. Heavy-tailed means that these tails of the distribution, they stretch out a little bit longer than for the standard normal distribution. It approaches normal distribution for large n, large sample size. Let me show you another Excel file that I show in my class. Okay, so here we have standard normal distribution, the orange curve. And this is a T distribution, the blue curve. Okay, so notice that it has heavier tails. So probability of extreme low values or the probability of extremely high values is larger than under the normal distribution. But that's a technicality. The important thing here is that T distribution, the shape of it is dictated by the sample size n. So here in this example, I have a super small sample of just 2 data points. I'm going to start increasing the number of data points and notice what will happen to the blue curve. 3 data points, 4 data points, 5 data points. Notice how the T distribution approaches the standard normal distribution. Can anybody guess at which point they will become almost indistinguishable? The magic number is 30. Remember, we talked about it when we talked about the central limit theorem. Central limit theorem says that the distribution of X bar, sample mean, is approximately normal for sample sizes 30 or more. So for all practical statistical purposes, T distribution is approximately equal to the standard normal distribution for sample sizes of 30 or more. And because of that, on this previous slide, when our sample size is larger than 30 or equal to 30, instead of T distribution, you are allowed to use standard normal distribution to get a very good approximation of your confidence interval. Okay, now what's what in the confidence interval? The confidence interval is an interval, some points A and B. What do we have in the center of the interval? In the center of the interval, we have the point estimate of population mean. Our unknown is the population mean, and at the center of the interval, we have the sample counterpart of what we are trying to estimate. In other words, we have the sample mean. Now, what do we have here and here? What it is that we add and subtract? What is this quantity? So we have X bar in the middle, plus minus some quantity. And this quantity is called margin of error. Margin of error. Margin of error is related to 2 things. So 2 things dictate how large your margin of error is going to be. Obviously, you want your margin of error to be as small as possible because you want your interval estimate to be as narrow as possible. Your margin of error is dictated by the confidence level. So this Z value will become larger the more confident you are. And the other quantity is basically, we've seen this before. This is the standard deviation of sample mean. The standard deviation of sample mean. Okay. This standard deviation of sample mean will become smaller for larger samples, right? Because sample size is in the denominator, so the standard error will fall if sample size is larger, so the entire interval will become narrower. So once again, larger samples are better for our estimation because our estimation will be more accurate. Okay, let's look at this specific example. We have a random sampling of a company's monthly operating expenses for a sample of 36 months. This sample produced a mean of $5,474 and a standard deviation of $764. With 98% confidence, the company's true average monthly expenses fall in what range? Let's understand what we are given. Okay, So when you're given a summary of data like this, try to understand what's behind the scenes, what's going on behind the scenes, and where we might have got this information from. So we have some monthly data. So maybe in month 1, we had expenses of $5,000. In month 2, we had expenses of $4,900. Month 3, $3,800, so on and so forth. And then we take this sample of 36 months and we compute their average. So we have 36 sample size and sample average is 5,474. And then we also compute their standard deviation, and it's 764. So this is what's given to us. So we are given information from a sample. And what we're asked to do is construct a 98% confidence interval for the population mean. The sample mean we do know, but what's unknown is the population mean. So we're going to have to use this formula. We are using sample standard deviation because we don't know sigma. We know sample standard deviation, but not the population standard deviation. We're also going to be using t-distribution here, even though technically we could use standard normal because our sample size is large, but it's okay. We'll use a more accurate approach. So this t-value is a high percentile of t-distribution, specifically since we have 98% confidence interval. This is 0.98, this is 0.01, this is 0.01. So this is the 99th percentile of t-distribution. Then we plug everything else into the equation, and we get confidence interval of 5,164 to 5,784. How do we interpret it? We are 98% confident that the true average monthly operating expenses falls between $5,164 and $5,784. We can also say something like, if we collect a gazillion samples of size 36, for each one of them, we construct a confidence interval, then 98% of the resulting confidence intervals would contain the true population mean value. And there is only 2% chance that the true population mean would fall outside of this interval. So now we understand what confidence intervals are all about. So what is hypothesis testing? What is hypothesis testing? Okay, we'll start with the same example. We are trying to estimate the average number of job interviews that master's students got this year in the USA. We are not going to use sample mean as a point estimate because it comes with a sampling error. And we are also not going to be using confidence interval because right now, I don't really care what's the range of values the population mean might take. I have something more specific in mind that I would like to test. I have a very specific hypothesis about the population mean that I'm interested in testing. For example, my hypothesis is that the average number of job interviews is greater than 10, or the average number of job interviews is less than 5. So as a result of my estimation procedure, all I really need is to get yes or no answer. Yes, our hypothesis is supported by the data, or no, our hypothesis is not supported by the data. Let's look at this example. A car dealer calculated that the company must average 4.8% profit on the sales of its new cars to cover its expenses. A random sample of 80 cars produced an average profit of 4.9% per car, and the historical standard deviation is known to be 0.3%. Let's summarize what we know. The goal is to make an average of 4.8% profit per car. We collect the data from 80 cars, don't count them because it's not 80, but pretend it's 80 cars. So in this sample, we compute the average profit per car, and it's actually 4.9. And you think to yourself, interesting, this 4.9 is bigger than 4.8. So is that it? Can we conclude that the true mean is actually greater than the target? No, we cannot jump to conclusions because this is just based on the data from one sample. There's no guarantee that a different sample wouldn't produce a smaller mean. So we can't rush to conclusions. But what we can do is, based on what we are observing, we are thinking to ourselves, I think the true population mean is actually bigger than what the car dealership says. It's actually bigger than 4.8. Let's test that. So we're going to formulate and test our hypothesis. Does the observed sample provide sufficient evidence to indicate that the sales policy is achieving true mean profit exceeding 4.8% per car? So we feel that the true mean actually exceeds this number, and this is what we're going to test. So that's how the statistical procedure works. First, we summarize hypothesis. Our hypothesis is that the true mean is greater than 4.8. We might be right or we might be wrong. If we are wrong, it means the opposite would be true. So in a sense, it looks like we are testing two parallel hypotheses. One is our research hypothesis. It's called alternative hypothesis. And the other one is called null hypothesis. Okay. Then in the step 2, we calculate what is known as the test statistic. So test statistic in this example is observed sample mean minus the hypothesized null value divided by sigma over square root of n. So actually, this is nothing but the z-score. Z-score in statistics is some quantity minus the mean of that quantity divided by the standard deviation of that quantity. And z-score value, the whole ratio, shows how many standard deviations a data point is away from the mean. If the absolute value of the z-score is high, it means we are too far. So if this test statistic value is too high, let's say 3, 4, 5, or 6 or more, it means that this sample mean is too high compared to the hypothesized mean value. So let's plug everything in into our equation. So we get the test statistic, the z-score 2.98. So on the standard normal curve on the horizontal axis, we locate this 2.98. It's to the right of 0, so it's somewhere here. So the rest of the statistical procedure, so here you can go in two different approaches. You can either use the critical value approach, or you can use what's known as the p-value approach. Critical value approach deals with computing the critical value. So we start the same way. We compute the test statistic. Here it is. And then, just like in confidence intervals, in hypothesis testing, we also need to know what our alpha is. Remember, alpha is the level of error that you're willing to accept when you're doing your estimation. Okay? So we compute the critical region that's dictated by this alpha of 1%. 1% is an area of 1% to the right of this distribution. And the point on the horizontal axis that corresponds to this 1% area is 2.326. We can get it very easily from Excel. So we notice that 2.98 test statistic falls inside the critical region. In that case, we say that we reject the null hypothesis because test statistic is in the critical region, and we conclude that, yes, we do have sample evidence that the true population mean actually exceeds 4.8, the null hypothesized value. And the other approach is actually very similar, but instead of comparing 2 points on the horizontal axis, we are comparing probabilities. So we look at the probability, the area of exceeding this test statistic value, and we call it p-value. And then we compare it with this alpha, 1%. And the rule is that if p-value is less than alpha, we reject the null hypothesis, and we conclude that, yes, this sample provides sufficient evidence that the true population mean actually exceeds 4.8. Putting it all together, step 1 in our example, we summarize our hypothesis. Okay, then we compute the test statistic. Then we proceed in one of two ways. Either calculate the critical region or we compute the p-value. In step 4, we say that test statistic is inside the critical region, or we say p-value is less than alpha, so we reject the null hypothesis. And our conclusion is we have sufficient evidence to conclude that the company is achieving policy of over 4.8% average profit per car. Notice that in all of these calculations, I use the same greater than sign. That's because this test is known as a right-tailed test. To my students, I say that in the alternative hypothesis, this greater than symbol looks like an arrow pointing to the right. Okay, there are also left tail test and two tail test. The main difference is in the sign that's used in the alternative hypothesis, and then the same sign is going to be used throughout the procedure. Okay, so what we talked about today is why we use samples for statistical inference, samples, not populations. We talked about law of large numbers, central limit theorem, and we looked at two examples of statistical procedure, confidence intervals and hypothesis testing. We used some examples. There are lots of extensions and applications of what we learned about today. Confidence intervals and hypothesis testing can also be performed for the difference in population means or difference in population proportions. The formulas are slightly more different. And this is used, for example, in A/B testing. Hypothesis testing is widely used to check if, for example, data follows normal distribution. Hypothesis testing is also central in regression analysis. Both approaches, confidence intervals and hypothesis testing, are widely used in predictions of the winner in presidential elections. In marketing research, they can be used to test if an online coupon helps boost sales, and many, many more. Okay. Thank you for watching. Now, any questions?
So hello again, everyone. So first of all, I want to thank Professor Chernobai for being with us and for her thorough presentation. And I see here that we already have some questions from the participants. And I want to remind everyone that if you want to ask questions to the professor, you still have time and you can ask them in the Q&A section here on Zoom. So I would say, let's start with the first one. Stephanie says, first of all, hi. I have a question regarding on what are the key differences between parametric and non-parametric methods, and in what situation would you choose one approach over the other?
Interesting question. So in my classes, we don't talk about non-parametric methods. So non-parametric methods means that you don't have a particular understanding of what the population looks like, the population from which you have extracted your sample data. So you don't have a priori understanding or a conjecture of what that population might look like, whether it's normal or something skewed, log normal, Weibull. There are all sorts of distributions out there. So non-parametric methods basically very frequently what they do is they rely on just working with sample and kind of taking samples out of the same samples, computing p-values by looking at the proportion of data in a sample and in repeated sampling that matches some criteria. So you're also asking in what situations would you choose one approach over the other? If you have a solid theory behind what you're doing, if you have a large enough sample, and if you're able to use central limit theorem, and the fact that for large sample sizes you can use normality assumption for your sample mean, for example, or sample proportion, something we didn't talk about today, then it's always better to use parametric methods over non-parametric, because non-parametric methods, there is more volatility, there's more uncertainty, and there's kind of more randomness associated with your results, whatever you might get.
Okay, so perfect. Thank you, Professor. And I hope that was helpful for Stephanie. So I would say let's move on to the next question by Daniel. He says, can the application of artificial intelligence and quantum science increase the confidence level in a survey while maintaining the same number of sample population?
I'm not sure what you mean by sample population. It's either a sample or a population. So I'm trying to understand what you are trying to ask here. So something about artificial, I'll just comment briefly on my opinion about artificial intelligence. So artificial intelligence is essentially you kind of let the data and the computer decide for you what's going on, what's the appropriate model. And I personally think there is a big value in artificial intelligence if you know how to give the right parameters to your computer, to your model, to perform the analysis. But in what I was showing here today is what's the fundamental statistical theory behind everything that we are doing. And it's also the theory that's behind all models that are used in artificial intelligence. And this is what I want my students to get a good grasp and a good understanding of before they move on to more complicated and fancy topics such as artificial intelligence.
Okay, so perfect, Professor. So maybe if Danielle wants to add on the question and specify what he meant by that, he can write this in the Q&A section and we can go back on it. So to move to the next one, the question is, can research models be applied to several searches, or is it necessary to develop a different static model for each search?
I'll be honest, I'm not completely sure what you mean by this question. Search models be applied to several searches, or is it necessary to develop a different static model for each search? I'm not exactly sure what you're asking me.
Okay, so since the question was from Danielle as well, maybe you can go back on that one and we can move to the next one in the meantime. So don't worry. The second one is there a curve in which trust begins to regress regardless of the increase in the number of population samples?
Is there a curve in which trust begins to regress? I think what you're trying to ask is, so we actually talked about this today, when sample size increases, your trust in your ability to make a more accurate estimation increases. And I think what you're asking, is there a situation where even when you increase your sample size, your trust in your results goes down? Well, it depends on the methodology and what it is that you're trying to do and what approach you're using. So sometimes, so for example, in a regression analysis, we are trying to tell if the regression coefficients are statistically significant, which is what would tell us that this particular explanatory variable is a good linear predictor of the dependent variable y. And so we want those coefficients to be statistically significant at the 5%, 10%, or 1% level. And sometimes if they are not statistically significant, one trick the statisticians do is they collect data from a bigger sample. But sometimes it happens that no matter what they do, no matter how large a sample they collect, the statistical significance of the coefficient does not really change. So sometimes sample size is not necessarily a remedy that would work. So there's no guarantee that it will deliver to you the results that you're hoping for. I think you're on mute, Alessandra.
I'm sorry. Okay, so I was saying thank you, Professor. And I want to move to the last question that we have for today, which is, how does any goodness fit theory tool help in getting an acceptable sample size?
So I hear two parts of the question. One is acceptable sample size. Another one is goodness of fit theory. So in my classes, we actually talk about what's the acceptable, what's the appropriate sample size, what should be the sample size, the ideal sample size in order to get our confidence interval to be within a certain range. We actually do this kind of stuff. So you can actually figure out exactly how large a sample you need to estimate in order to get a narrow enough confidence interval or test statistic of a certain value. So you can actually play with sample size selection to achieve to a certain level the results that you want. And then another part of your question was about the goodness of fit test. So goodness of fit tests are used in a variety of situations in statistics. One of them is in regression analysis. And so there are two types of goodness of fit test: in sample and out of sample. And it's very important to emphasize both, especially to students who are not very familiar. So very often in regression analysis, students focus on R-squared or adjusted R-squared and maximizing that. And they think, oh, my R-squared is 0.99%. I have a great model. But then when you take the same model with the same coefficients and you apply it to a different sample data or data from a different period in time, then your model miserably fails. So what's important here is that just because your data works well in sample doesn't necessarily mean it will work well out of sample. So there are a variety of techniques in statistics, for example, in regression modeling, especially with time series data, when you test your model using a shorter time interval, and then you reapply it on a different time interval and see how many times your model failed and how many times your model gave you similar results. So this is called out of sample.
Okay, perfect. Thank you, Professor. We have some last minute questions that are coming in. So we're going to move to the next one, which is it possible to arrive to 100% in a probability?
Excellent question. I was going to talk about it today, but then I was looking at the clock and I realized I can't quite talk about it. So notice that today, throughout the presentation, I was talking about this level alpha, the level of error that you're willing to accept whenever you do your estimation. So let's think about confidence interval. Why is it that we never want to be 100% certain? I give a simple example to my students when I teach this topic. I ask a student, how confident are you that the first person you see when you leave this classroom is going to be between 5 and 5.5 feet tall, a narrow interval? And he says, let's say 60%. Then I widen the interval and I say, how confident are you that the first person you see is going to be between 4 and 6 feet tall? And he says 80%. Then I say between 3 feet tall and 7 feet tall. He says, well, 95% confident. Then I say between 0 feet tall and infinity. And then he says 100% confident. What's important here? The more confident you are, the wider the interval is going to be. And it's bad because if you're 100% confident, then your interval is so wide, it's not informative. So there is a trade-off that you have to play with. So there is a trade-off between being very confident and also having a narrow interval, because you want both. That's why in hypothesis testing and confidence intervals, you'll never be 100% certain. You will never get a certainty level in your estimation beyond, probably the highest I've seen is like 99.999%. It's almost as good as 100%, right? But it's not 100%. And believe me, that tiny 0.001 makes a huge difference, okay? So you will never be asked by your professors to construct a 100% confidence interval. Without doing any estimations, you can just give the answer from minus infinity to plus infinity.
Okay, perfect, Professor. So I think we have Daniel back with us. Going back on the first question that he asked, which is here, I can read: statistical models for financial market research can be applied to analyze a population or for risk analysis, or does each research need a different statistical model?
Statistical models for financial market research can be applied to analyze population or for risk analysis. I mean, there are all sorts of statistical models and models that are applied in finance. The same models can be applied in engineering, marketing. So the models that I showed you today, they are very commonly used regardless of the discipline. So I don't know exactly what models you're talking about in financial market research, but there are all sorts of hypothesis tests that you can make based on your data. Today we covered hypothesis tests for the population mean, but there are also hypothesis testing for the difference in two population means, or difference in two population proportions. There is also a hypothesis test for variance, standard deviation, hypothesis test to check if financial data such as stock returns data truly comes from a normal distribution. There are varieties of tests that exist, but if you understand the main principle behind how each test works, you'll be able to understand how to form other tests in your financial or other research.
Okay, so we have one last question by Carlos, which is, how is the consequence of changes of number in samples during the development of a master project? And he gives us an example. He says, I would like to use 200 bovines, but now I have to use 140.
100, it depends on a setting. 140 can be actually quite large. Like if you think about medical research, a lot of medical studies, they're based on a sample of just 20, 30 patients. A lot of studies in scientific research are based on very small samples. You just need to know how to use those samples wisely and how to make the statistical inference in the way that it's, trustworthy, right? So 140 seems like a decent enough sample size. 200 is definitely better. It depends on whether sample size of 140 would give you a statistically significant result that you're looking for in your data. And also, if a sample of 140 observations is truly random sample, it's still better than having a non-random, a biased sample of 200 observations. This is something that we also have to be mindful of. A smaller but random sample is always better than a larger sample but biased sample, because a biased sample would give us biased results.
Okay, perfect. So we're done with the question, but we have one last one, which if Professor Chernobai allows me, I'd like to answer, because the question is, this masterclass will be available to review, and the answer is yes, because tomorrow you participants will receive a thank you email with a link to the recording of the session, so you'll be able to go back on the lecture that the professor gave to us. And also you will have now in the chat a link to request a certificate of participants by Docsity for being here with us today. So I want to thank Professor Chernobai for being with us today and for her thorough presentation, and also everyone for joining us. And I hope to see you again soon to the next webinar organized by Docsity in partnership with Syracuse University. So bye everyone and have a nice day. Bye, Professor. Thank you so much.
Thank you. Thank you, everyone. Bye-bye. Have a nice day.